very much. I think I gave a different title, and I probably just forgot to change it, to update it. It was something like high temperature freezing. But what I will talk about is something you probably are familiar with, partially, at least some of your listeners are. I believe some of my co-authors gave a talk on their previous paper here, if I'm not mistaken, or am I confusing it with a different series? In any case, the topic will be how we can have order at high temperature, because the lore was for a long time that this is impossible, and there are even theorems which say it's impossible. So I will talk about some simple models, minimal models of which realize this, and this is the topic of the first paper here, which is now on arXiv already. And shortly after that, I also, along with some collaborators in Durham, which are here, these young gentlemen here, and young collaborators here, is the topic of the second paper, where we've managed to prove some concrete things about a particular class of such models. So without further ado, here's the summary. I will first give a gentle introduction into high temperature freezing and what does this mean and how we can even expect this to hold, given some basic thermodynamics. And then I will talk about something which I call generalized Ising models, because they're very similar to Ising models, except that instead of Ising spins, which are plus and minus 1, we just take them to be non-negative integers. This will be very important, that the local configuration space is infinite. Part of this model has been discussed by my collaborators, by some of my collaborators in previous publications, so I will review that, and I will try to give some intuition why this should hold. Then I will also discuss very briefly some continuous gas models, just to show that this is not particular to lattice systems or discrete systems. Continuous gas models also have some kind of a Hamiltonian dynamics with them, whereas for discrete lattice models, it's not clear whether there is such a dynamic, so one could object to that. So mostly I will discuss it just to illustrate that this is not particular to some discrete models. And finally, I will discuss a little bit about the second paper. I will not go too much into details because my understanding is that my postdoc Enrico Andriolo will also give a talk in this seminar series later, and he will probably give you much more details. I will kind of just give you an overview of this and what I think are important points. And then we will conclude. So please do ask questions, as many as you like. I can slow down if there are some questions. Please don't hesitate. So without further ado, why? Let's just review. This is well known to most of you or all of you, that why do things melt? Things melt because at high temperature, at finite temperature, we're minimizing the free energy. And if temperature is very high, the free energy naturally attains its minimum by maximizing entropy. And therefore, at very large temperatures, all bonds kind of are irrelevant. We are sampling the configuration space equally, so democratically, and such a configuration space is typically not ordered, or is not ordered unless because interactions are irrelevant. This is also the reason why we need to cool down our engines or our computers, because the material depends on the fact that we have solids. Solids will melt if they're heated too much, so we have to cool them. So if we could reverse things somehow, if we could have order at high temperature, this potentially has tremendous application. But can order exist at high temperature? And instead of giving you a complicated, well, it's not overly complicated, but instead of going into math why this can work, let me give a very simple example, a cartoon example, a party example of a gas of balloons, meaning I'm viewing balloons now as particles, and it's a model of a gas. Balloons will be in a vacuum just for simplicity. And if balloons are small, they can kind of go past each other. Maybe they bump here and there, but there's certainly no long-range order of these balloons. At least this is the picture at low temperatures. But if you increase the temperature, balloons will bump into each other more often. The temperature inside the balloon, the gas inside the balloon will expand because the temperature inside the balloons is increasing. And at some point, they're going to densely pack, which is kind of like forming a lattice of balloons. So this example is good because it gives clearly an illustration of all these examples I will show. We will be coming back to this this kind of similar structure. And what happened here is that as the temperature increased, the gas inside the balloon expanded so that it maximizes its entropy because it now explores a larger volume of its configuration space. However, because there's a barrier between balloons, the price to pay for this was order, because now balloons press on each other and make this lattice. So even though the entropy increased, the order was formed. So this law that order means low entropy is a little bit of a fallacy. It's not always the case, although in most cases it's true. It need not be true. Sometimes you can pay the penalty of order in one dimension of the configuration space to increase the overall entropy of the system. And that is going to be the topic here. This is why this kind of order is called entropic order. Now, to make this more concrete, let's see how this fails for systems like the Ising model. You can make this more precise for any, so for many classes of systems and prove some theorems here, but let us just look at it, why it fails for Ising model. And the reason why it fails for Ising model, sorry, not sure what I did here. The reason why it fails for Ising model is because the probability of any Ising spin is proportional to the Boltzmann weight. And if beta, which is the inverse temperature, is set to 0, then all probabilities are equally likely, because this Boltzmann factor can be just taken to be identity. Okay. So whenever you can do this, you can say that there shouldn't be high temperature order, because you will just uniformly explore all of the configuration space. If you make a naively innocuous modification, and instead of taking spins to just take 2 values, instead they can take any integer value. Now your Hamiltonian is not bounded from above anymore. And for each temperature, there exists very high energy states which cannot be ignored, and you cannot just replace this Boltzmann weight with identity. In other words, if you were to do this, then this partition function wouldn't even be well defined in the case of finite volume, and that is illegal. And that, in fact, such similar models, which I will briefly discuss, were introduced in this paper, this recent paper by Han, Huang, Komargotsky, Lucas, and Popov. this is the class of model I will refer to as generalized Ising models, because they are very similar to Ising models. There is a parameter that you will see in a moment. So this is the models that I will discuss.
Can I ask a question?
Yes.
So is it fair to say, just to be sure that I'm understanding correctly, is it fair to say that essentially what you're doing is increasing the energy of the single site in a way that essentially you push the temperature to what it converts to 1 as E2, so the boson weight converts to 1 is essentially pushed to higher and higher temperature, and if you take like infinite energy, essentially it's pushed to infinity. Is it more or less this what you are doing?
I'm not exactly sure what you mean by what is pushed. So what's going to happen is that there's never going to be a temperature at which the material melts. So in that sense, nothing is pushed higher and higher. The system actually becomes more and more ordered the higher the temperature you take. So in that sense, it behaves very differently.
Okay, I see.
I will try to explain in more details this thing. So let's make things very concrete. We will consider this model, and if you look at it, it's very similar to the Ising model. The only difference is that now instead of Ising spin sigma, I will take some integers or non-negative integers, which can take values 0 to infinity. And for the purposes which will become clear, I will also introduce some parameter p, okay? Importantly, both parameter coupling u and mu here have to be positive. If this is not the case, and in fact, even if mu is equal to 0 and u is positive, the model is not well defined because the partition function has directions where kind of you have, you could, to see that something is not well defined, let's say that I'm putting all spins to 0 and just one spin I'm summing from 0 to infinity. Then this term completely vanishes, and if this one is 0, the partition function is not well defined. It diverges, in other words. So both parameter u and mu, let me try to erase this. Not sure how. So both parameter u is greater than or equal to 0, while mu has to be strictly greater than 0 in order for this model to be well defined. And the claim is that this model can have order at high temperature depending on the value of p. And let's try to understand how this happens. So firstly, if we take, in order to gain some intuition, we will use mean field theory. And in mean field theory, we can just put all of these spins to be the same if they are in the gas phase, okay? The gas phase I use as a synonym for a phase which has no order, gas or liquid or whatever you want. So an ansatz for a mean field theory approximation is that all spins are the same. Now, if that's true, then because this first term penalizes these spins as u n bar to the power of 2p, then the maximum value of n, of this uniform n, will scale as t over u to the power of 1 over 2p. Otherwise, it will be exponential. Anything larger than this value will be exponentially cut off in the partition sum. Okay? Now, contrast that to a different ansatz where instead of placing spins, putting a mean value of spins everywhere the same on the lattice, I instead put it in some kind of a checkerboard pattern. And for the purposes of this discussion, I picked the lattice to be some kind of a square lattice in 2D. And I just occupy only odd sites or even sites, if you wish, which are labeled here. Now, if I do that, then the first term and everything on the rest of the sites, on these white sites, is just n is 0. I just place it as an ansatz, right? But now notice one thing. Now these spins can take a much larger value because they are only suppressed linearly with n. Well, depending on p. Of course, depends what p is, but depending on what p is, these spins can take a much larger or smaller value. In any case, it's a different scaling with t. Here we had some 2p root of t, and here we have scaling which is linear with t. So the point that I wanted to make is that the entropy per site, per occupied site, is very different. In the case of a gas, we have the entropy which is 1 over 2p times the log t. Whereas in the case of this, what I will call a solid, we have per occupied site, we have that the entropy scales logarithmically with t, with the unit coefficient. Okay, is this point clear? Are there any questions here? What I'm trying to say? I'm simply trying to say, because of the repulsive interactions, when I'm trying to fill everywhere uniformly the lattice, they clash, right? This repulsion forces the maximal spin to scale potentially slower with temperature. If p is larger than 1, as we will see, it will be slower scaling. Whereas if we occupy only half the lattice, such that occupied sites are surrounded by empty sites, then I can go much higher in principle with the occupation. But what I sacrifice the fact that translation symmetry is no longer realized in this state. Okay. If there are no questions here, let me move on. So that's the essence of why these models have potentially have entropic order. Now, the only thing that you have to here account for is, of course, that in the right-handed case where there is some order, there's spontaneous breaking of translation symmetry, I have half the occupied sites. So per occupied site, the entropy is log t over mu on the right-hand side, but half of the sites are empty. So the total entropy density is 1/2 of log t, versus on the left side, I have 1 over 2p log t, right? And I'm taking temperature to be very large, okay? So now this is very simple. Now all you have to do is you have to compare which entropy is larger, who wins at high temperature. And it's very easy to see that if p is larger than 1, then the right-hand case wins, order wins at high temperature. Okay, this was the basis of the paper on that is cited here. That was the motivation for all of these models. So the point is that if this exponent here p or this interaction, this repulsive interaction is strongly repulsive enough that we will always have order at high temperature, and repulsive enough means that p is strictly greater than 1. Whereas if p is less than 1, we have a boring case where gas dominates. Now, I want to make a little bit of a teaser now. I will later show you that even this gas phase here for p less than 1 is not so boring. There's something interesting going in even in this gas phase, although we have not explored this. But keep this in mind. P larger than 1, always order at high enough temperature. P smaller than 1 seems to be boring gas, and it has the usual behavior that there's no ordering at high temperature. But there's something interesting happening here. Okay, so that's the mean field theory argument. Okay, But it turns out that in these models, if you do it carefully, and if you compute corrections to mean field theory, that they are large. They grow with temperature. And therefore, mean field theory is not really justified. However, these gentlemen here did lattice simulations as well, and found that that there is order for p equal to 2. They haven't explored other cases, but it seems to be very robust. So what we did in the subsequent paper is ask the question, what happens when p is equal to 1? And when p is equal to 1, then it's more subtle, because both entropies of the ordered and the disordered phase scale the same with temperature. But as you can see here, there is different parameters u and mu. And now which one wins when p is equal to 1 here depends on u and mu. And it's very easy to see that if u is much larger than mu, you should have that order wins. And to check that, we did lattice simulations of this model. And on the right, you will see an order parameter as a function of u for temperature equals 1,000 mu here. Everything is in units of mu here. So mu is set to 1, so that I count all of the units in, so all dimensionful units are in units of mu. And as you can see, these are lattice results. These are lattice points here for various lattice sizes. As you can see, if u is small at this high temperature, then there doesn't seem to be order. The order parameter is 0 for this symmetry breaking. And then at some point, it starts rising. And you can check critical exponents. You find that they are Ising-like and so on, because the relevant symmetry which is broken is Z2. It's a translation symmetry mod 2. On the left, you can see some configurations, typical configurations of this model, and at this temperature. And you see kind of here you have a gas, and if you increase u, you start around u around 1/2. You start seeing this checkerboard pattern, which indicates a solid. But an interesting thing is that if you do this in mean field theory, which is not supposed to be reliable, you get results which are very, very close to the actual results. Okay, so that's a little bit of a puzzle, and it's not clear why they're even close. Now, and the question now is also, can we understand why this is close? And I will now discuss a model in which we can understand systematically what happens. And this is a model similar to the one that I introduced. The only difference is that instead of this n just being an integer from 0 to infinity, we write it as uniformly distributed sum of uniformly distributed integers n x alpha. We call this the k-color arithmetic Ising model. So this model we call arithmetic Ising model, just because it spells aim, I guess. We were trying to think of some interesting name. And this is kind of like having k colors. Now, the benefit of writing it this way is that one can rewrite the free energy in terms of some continuous field, which becomes continuous when k goes to infinity. And moreover, it has a factorized integer k in front, allowing a saddle point approximation. So if k goes to 1, we get back our original model, but it allows a systematic large k expansion. Okay. And miraculously, it seems that in this model, independent of k, it seems that these offending large fluctuations that may invalidated mean field theory cancel. And moreover, this critical U at very large temperature, as you can see here, there was some critical U, which was very close to 1/2. This is in units of mu, if you remember. Turns out to be have a correction which is a 1/k correction, but which also vanishes as t goes to infinity. It is a log t over square root of t correction. And it seems that this is true to all perturbative orders in K. We have some arguments that this may be true to all perturbative orders in K. So now the question is whether these curves, which are numerically observed here, whether they converge to the mean field theory result, critical value of U over mu. And we try to simulate at higher temperatures here. And this is the lowest temperature we simulated. This is 10 to the 3,000 mu's. This is in units of mu's. And you see this order parameter starts developing at U over mu values of something like 0.63 or something. But as you increase temperature up to 100,000 mu's, you kind of start approaching this U over mu equal 1/2 mean field value, but you don't quite get to it. I mean, at least our numerics never got to it close by. So it's possible that at very absurdly high temperatures, somehow this approaches. But that's something that we couldn't really resolve. It seems that this large K expansion indicates that that the phase diagram looks something like this. In other words, that as you increase temperature, you may end up in a solid phase as long as U over mu is larger than or equal to 1/2. But this point here may be a little bit smaller than 1/2. Could be, a little bit larger than 1/2 as well. So that's at least what we have found so far. Are there any questions at this point about this model? Okay. Now, but keep in mind one thing, though, that even though we computed everything in this large K expansion, and we have some arguments why this is true to all Ks, even the large K expansion is unjustified at fixed K but infinite temperature. So technically speaking, it's not if T is too large, much larger than both mu and U, this expansion also should fail at fixed K. At infinite K, this is robust, but we are not at infinite K. We want to extrapolate to K equal 1. And in the most recent paper, now this I will just say without saying anything why this is so, because it would take me too far afield. But in the most recent paper with my postdocs and students, we actually proved entropic order of this model. And we managed to prove it for U sufficiently large. We don't know exactly how large it has to be, but it's some finite but large U. However, this proof also seems to indicate, although it's not a proof anymore, but it seems to strongly indicate that maybe the phase diagram of this kind is actually true, that a solid at very high temperature persists for all values of U. But for very small values of U, the transition temperature is very large. Now, we don't know how to prove this, And I want to give a first take-home message of this talk and some future prospect. How we can check this, it's not clear. So is there some analytic method where we can distinguish between the two scenarios, or maybe even a numerical method? Because the problem with numerics is that we have to approach infinite temperature by increasing T, but we don't know how high T has to be for us to distinguish between these two things. So could we somehow find some dual model, for example, where we can expand around the infinite temperature point or anything like that? So this is the first thing kind of for the outlook. We've understood many things. By now, it's completely clear that if U is sufficiently large, this model has high temperature order and freezes at high temperature. It is not at all clear what happens at small U over mu values. Okay, given the simplicity of this model, I think it's a worthy cause to settle this question, but I don't have the answer.
Tim, can I ask a very quick question? So,
yes,
just to understand correctly, so basically from the numerics, you didn't see this, but you proved analytically, or if not analytically, you proved that the thermal order is achieved in this model. You don't know the temperature, but
yes.
the temperature
So
is it.
So for large enough U, we both see it numerically. You see here numerically, this is solid here. Okay, whenever this is the order parameter. So when the order parameter is non-zero, that should be the solid phase. So for large enough U, both numerics, mean field theory, okay, which was with in the paper with Huang, Komargotsky, Lucas, and Popov, mean field theory, large K expansion, this K-color arithmetic Ising model that we developed, they all consistently show U large enough, U over mu larger than, at least much larger than 1/2. If U over mu equal to 0.6 is already sufficient, has order. Then in this second paper, we proved, so that all of these methods were not, although very, very strongly indicating this is true at infinite temperature, at arbitrarily large temperature, all of these methods had problems taking this limit. So in this second paper, I will review some ideas of the second paper in a moment, but in the second paper, we prove that if U over mu is large enough, we don't know how large it has to be, but some finite but large value, this is indeed what happens. But as a side effect of this proof, there's one minor thing that we cannot prove for low U, but it seems that at infinite temperature, order persists. Now, I don't know, maybe there's some subtlety in, it's not a proof again, but this second paper seems to indicate that maybe for all values of U, we have order. It's not a proof, but it's strongly indicating that that's true. I will tell you what we can prove in this. If we take temperature strictly infinity, then we have configurations which are either order A or order B. We never have domain walls between them. They're all killed at infinite temperature. Where the proof fails is at finite temperature, we don't know how to argue that these domain walls don't immediately. So infinite temperature is just not physical. So, our proof at infinite temperature, I don't know what it means. But it's very difficult to imagine that when you go from infinite temperature to finite temperature, that all of a sudden you have disorder, right? Because you usually have domain walls and they have some finite tension. This tension goes to infinity as you send temperature to infinity. So that's the step which we cannot prove. But to my mind, it strongly indicates that order may be true at high enough temperature for any value of U. Okay. I'm sorry, I'm being very vague here because there's many details that I would have to present to make a solid argument. And since my point that I want to make, all these approaches for low U seem to have a flaw. And we really need something to decide what happens at small u, okay? Because all of these have a flaw there. There's a corner here, which we are.
Tim. Hi,
Yeah.
it's Fyodor Popov,
Hey,
not
Fyodor.
Popov.
Yes.
So I just wanted to ask you, because I asked you this question over email, but you didn't reply to me. But there is like the Bruchian theorem, right? And we have like, there is like a lemma for the Bruchian theorem that applies for any system, right? So did you try to apply it and see where does gas phase happens?
No, the answer is no. I didn't try.
Okay, because I think it could like hint how it goes to. Yeah,
Fair question. Fair question. I think we should talk about this because I think this is it may be something I'm misunderstanding. Okay, so but I think that this is something that needs to be settled.
Yeah, just like there's some general lemma that just immediately tells you where the gas phase exists, and it could just tell you where, just rule out where the gas. It can put where gas state must exist. That's the only thing I'm telling. Okay.
Okay. Okay, let's talk about this. I'm very interested to hear what you think. And I'm sorry for not answering your email. I don't think I saw it. Maybe it got lost in the pile of unread emails. Okay. Now, so let me summarize the AIM model. What I said, some things I said so far, and say a couple of other things maybe. So certainly entropic order, if U over mu, if U over mu is sufficiently large, is achieved at high enough temperature. So this model, if U over mu is large enough, approximately larger than 1/2, then if you heat this model up, you will get a solid phase. So that seems to be beyond question. We now have several approaches and one rigorous approach, which I will briefly discuss. Sorry, this is supposed to be much larger than 1 or larger than 1/2. So mean field indicates this. Large K is consistent with this large color model. However, they have problems at high temperature. It's not, perhaps there are some loopholes here. But the most recent paper, as I mentioned, indicates that order may persist for all U. And this is something that we need to keep in mind. Now, another thing that I didn't mention, but this model can be generalized to a quantum model. You can add, you can replace n's with occupation number of bosons, add some hopping terms, and this is like a version of the Bose-Hubbard model. And Zohar Komargodsky pointed out that these models appear also in some supersolid models from 2009. So that's an interesting observation. I don't know whether it's relevant to entropic order, but they appeared in the literature before. So that's kind of the summary of this model that discussed so far. Now, if there are no more questions, let me pause and see whether there are questions at this point, because I don't want to rush through.
So very, very quickly, maybe. So when I consider U over mu to be much bigger than 1, basically it's like I'm saying I'm getting rid of my mu deformation from the model. So basically I'm just using the regular nearest neighbor interaction.
Yeah, it's like in that case, you have a hardcore lattice model, basically. So neighbors are vetoed. So models have been known which have constraints. So this is kind of a model with a constraint. In that case, it's completely clear that at high enough temperature, what you're trying to do is you're trying to populate at high enough temperature, you're trying to populate your lattice, but neighbors are not allowed. So then it's obvious that there's order. Such models appeared in the literature. I should have probably mentioned that So you can have, for example, a hardcore sphere model, which is completely independent of temperature, which could have order. So models with constraints were known kind of to have at least persistent order at high temperature. I guess what is interesting here is that at temperatures much higher than the interaction scale, right? Because U is the interaction scale. If you fix the interaction scale, you would expect at very high temperatures that all knowledge of interaction washes away. That's not true. And that's the most interesting thing about these models, that there's always memory of interactions, no matter how much higher the temperature is. But thank you for the question. It's it is a good question. Okay. So what I wanted to do next is discuss some continuum gas models, but in view of time, I'm going to skip this. The continuous gas models that I was going to discuss are kind of, in many ways, very similar to the balloon model that I showed. Okay, I was just going to show some very concrete formulas. Maybe very briefly, the model that I had in mind is kind of like a spring gas model, where you have a gas of springs, which have an intrinsic size. And if you make the interaction some function of distance times the size of the two springs, or some kind of polymers if you want, if you cook up some kind of a interaction like that, you can easily show that that these models have order. So I will skip through this just because I don't want to jump now, given that I took so much time. I'll give you just one very simple model with some kind of a Gaussian interaction. And I will show you just the animation of a Monte Carlo simulation, if I can get it to play, as I increase the temperature. So this model kind of is a complete gas and nothing interacts at low temperature. But as you increase temperature, what happens is that these internal degrees of freedom, these sizes of springs, which are here labeled by the color, start exploring that space of the internal size of springs, or it's this internal degree of freedom. And because the interaction grows with the size of this internal degree of freedom, you see that they start repelling, and you can kind of see the hexagonal lattice here forming. Now in 2D, lattices will never form because of Mermin-Wagner theorem, but such models can be built, and I don't want to spend too much time on this. It's very similar to what I already spoke about in these arithmeticizing models and so on. If you want to know more, you can look at our paper. Now, in the remaining 13 minutes or so, I want to talk about this second paper where we've proved the entropic order also for all of the generalized Ising models, and in particular for the p=1 model, which we call the arithmetic Ising model. And I just want to give you an overview of that paper. As I said, Enrico, I believe, will give a talk in this seminar series. I'm not exactly sure when, I think June, or maybe it's July, I forgot. So he will talk in much more detail about the paper. I will just give a very brief overview. But before I do that, I have to talk about a little bit about graph theory, because it will be important in what I will say. And in particular, the notion in graph theory, which is called independent sets. Now, if you have a graph, which I drew an example here of a graph, an independent set is simply a set which contains vertices which are not each other's neighbors. So for example, to construct an independent, this is an independent set. I can just take one node, and it's a set, which is an independent set. But I can if I take two nodes which don't neighbor each other, like here, that's also an independent set. And I can just keep going like that until I fill the whole graph. Now, if you just do this, one of these graphs where you just take a node, include it in the set, exclude all the neighbors and fill the whole graph like that. This is called the maximal independent set. Okay, so you can do this in many ways, in all possible ways. And in all of these cases, we found that the size is 3, but we found one example where the size of this maximal independent set is 4. And graph theorists call this the maximum independent set. In other words, the maximal independent set is a local maximum, whereas the maximum independent set is the biggest of those, okay? The largest one, okay? It's a little bit of a non-perturbative terminology. And the label for the maximum independent set is typically given by alpha. Here I put alpha C. C is for connected graph. So sometimes I will use the label G, and sometimes the label C to indicate that the graph is connected. So in this case, alpha of C is the value of the maximum independent set, which is equal to 4 in this case. So now let's talk about this notion of maximum independent set in ways that we will use it in a moment that will be useful for us. So you can think of the maximum independent set by associating integers 0 and 1 with the node, which I will label by x. So this is a vertex of a graph. And then you can impose the constraint that the sum of these numbers on neighboring vertices has to be less than or equal to 1. Meaning that if it's 1 on one, it has to be 0 on the other, or they can both be 0. Right? This is just a constraint that there are no neighbors. If the site is occupied, everything neighboring it is unoccupied. And then you want to maximize this quantity, sum over all p's, sum over all occupations, right? And you can define this as a maximum independent set. That's exactly what we said. It's just formalizing it a little bit. Now, what's very important about the maximum independent set is that it's an NP-hard problem, meaning that the most optimal algorithm to find the maximum independent set of the graph, the most optimal known algorithm, I should say, probably, is exponentially, takes exponentially long in the size of the graph. You basically have to just do what I did previously. You have to label a point and then exclude the neighbors until you find the maximum one, okay? So you have to do order n, where n is the size of the graph steps. Now, similar to or related to this problem of the maximum independent set is the maximum fractional independent set, okay? Now here, everything is almost the same. The only difference is that instead of p equals 0 or 1 being integer, I allow p now to be any number between 0 and 1, any real number between 0 and 1, 0 and 1 inclusive. Okay? So this is called the maximum fractional independent set. And this problem is much easier. This problem can be solved in polynomial time. Okay? So this is some notions I will need from graph theory to apply to this problem of generalizing. Are there any questions here about the maximum independent set and the maximum fractional independent set, or is everything clear? Okay, good. If there are no questions, let me continue. Now, just a couple of examples. So, for example, the maximum independent set of this graph, which is like a triangle, is just 1. I have only one way to pick a node, which is the independent of any other ones that I pick. But the maximum fractional independent set is 3/2 because I can populate with 1/2 all 3. You see the sum of every neighbor is not larger than 1. And that's the difference, right? So for some graphs, you can find that, here it's supposed to be also 1 here. For this graph containing only 2 nodes, they're the same. In fact, you can show that for any bipartite graph, they're the same. This is another bipartite graph. But there exist non-bipartite graphs where they are different. So it's a different problem in general. Okay. Now, why am I saying all of this? The reason why I'm saying all of this is that we can use this, leverage this problem or leverage graph theory by looking at the generalized Ising model, which is, I am giving the Hamiltonian here again, in the following way. We're going to associate a weight of a configuration given in terms of integer n with focusing only on whether the site is occupied or unoccupied. So this is the occupation number. A site is occupied if n is 1 and larger, and it's unoccupied if n is 0. Okay, so if n is 0, then s is 0, and s is 1 otherwise. So that way, we can associate each configuration with some kind of an induced graph. So if these nodes are occupied here on the left, which are shaded, then I associate with the configuration of my theory, we associate some kind of graphs, some kind of, in general, disconnected graphs, but I can associate some kind of a weight with each connected component, because connected components don't talk to each other, right? Because we are, everything which is S0 does not breaks the interactions. Interactions only happen if S is non-zero. So I can analyze configurations which are labeled by graphs of occupied spins here. In other words, I can write the partition function as a sum over so what I wrote here is the weight of this configuration, which decomposes as a product of weights of connected graph configurations. And then my partition function is just a sum of all such induced graphs, right? Sum over all activation variables S0 and 1, which induce a graph. So now all we have to do is we have to analyze the weights of these induced configurations when sites are occupied or unoccupied, okay? If we have to then distinguish between the weight of graphs which contain only one node, which are very easy to compute, right? Because you have just one node, all interactions are 0. So you just sum over n, and at very large t, such configurations carry weight t over mu. Okay, but what is now more complicated is how do you compute configurations associated with more complicated graphs? And this is the essence of the second paper with Andriolo and Nguyen and Richards. And the most important result of that paper is that all these weights of the connected graphs with nodes, which have nodes larger than 1, number of nodes is larger than 1, scale like this with temperature, where the exponent here is the size of the maximum fractional independent set. Okay, so in other words, all these occupied, all these connected graphs, which you're supposed to sum over, all of these configurations in the partition function you're supposed to sum of, their weight is completely dictated at high temperature by the size of the maximum fractional independent set. That makes kind of intuitive sense because you're trying to distribute the excitations over all of the connected graphs. right? And the optimal way is this maximum fractional independent set. You want to distribute them in some sense equally so that they have the highest, give the highest weight. Now, what is non-trivial perhaps is that there's also a log correction, which I will mostly ignore in what follows because it's not important. But it's curious to notice that the power of the log has to do with some moduli space of the solution of this maximum fractional independent set. Because fractional independent set assigns some real number between 0 and 1 on each node, it could have a moduli space of solutions. And so there are some log corrections associated with this, but they will not be important in what follows. Good. Now, in order to see which configuration is the most dominant, because now you know that each configuration in the partition function labeled by these activation variables, this spin 0 and 1, which tells you whether the site is occupied or unoccupied, has the following scaling. Now, I did some manipulations here because there is, if you induce a graph like here, so for example, for any given configuration, I have some kind of a graph G, which I called H here, just because G is the whole lattice. So, so then you can do some manipulations and find that because isolated points are special, they will appear separately. And the weight of this configuration will have this maximum fractional independent set. So now the question is, which configuration is maximal? Well, the maximal, or the most dominant one, is the one which maximizes this exponent. So then you are asking a question, which subgraphs have the highest temperature power, right? So you have a whole graph G, and a subgraph H, and you ask which one is the most dominant. And you can prove that if P is larger than 1, and if the graph is bipartite, that the graph that dominates is the one of the maximum independent sets. So I didn't write it here, but it's basically on a square lattice, it's our checkerboard. It's the one that doesn't have any neighbors. Okay, so that's a crucial part of the proof that you can show by deriving this formula, that the checkerboard phase on the square lattice, it would be a checkerboard, but the proof goes beyond the checkerboard. For any bipartite lattices, you have that it's for P larger than 1, it's the analog of the checkerboard. How much time do I have? I'm almost done. Good. Now, even before proving that order happens, what I want to emphasize is that you can show by using this dominant configuration that the equipartition function looks something like this. Okay? That means that at very high temperature, your average energy is proportional to temperature, but there is some complicated coefficient here. And if P is small enough, you can show that this coefficient is just 1. This is what you usually expect from normal gases. If temperature is very large, then all of these sites behave independently. There's n degrees of freedom. This is here equipartition divided by n, if you see. So this should be 1. Coefficient should be 1 times n. But for P even larger than 1/2, you don't have the usual equipartition theorem. Here is the solid phase. But the gas phase for P between 1/2 and 1 is still an unusual gas phase. There are some correlations at very high temperature. Right? It's not the usual gas. This is one point that I wanted to stress. Okay, so because I'm out of time, let me not bore you anymore with some details here. The point I wanted to make is that we are able to prove concrete things at very high temperature for these generalizing models. But one of the side effects of this proof is that even for p smaller than this marginal p, this thing which distinguishes high temperature solids from high temperature gases, these gases seem to be non-trivial in some sense. We haven't explored this in details, but I think that this deserves exploration. So with that, let me just give you the conclusions and apologize for going over time and open for questions.